Hello student, to the Foundation of Classical Electrodynamics course under module 2. Today we have lecture 33, and in today's lecture we will continue the different aspects of this electric dipole. We have class number 33 now. And the thing today we are going to calculate, the first thing is the potential energy. Last I mentioned that. Potential energy of a dipole placed in an external electric field. So, there is an external electric field and I place a dipole, and we need to find out that what should be the potential energy. Potential energy we discussed earlier. So, that thing we calculate. So, let us do it quickly. So, we have a dipole here. Say this is minus q plus q, and this length is a vector d, and the location it is located with some origin like at point say r, and r say plus d. Okay. So, the external electric field E described by the potential phi r. So, I can write this external field with that potential. So, this is this quantity. So, this is the potential phi that we are going to experience by the dipole, and if that is the case, we know what should be the potential energy, and we know the potential energy is charge multiplied by the potential it will going to experience. Last day we calculate, last to last class. So, for the dipole it is simply whatever the charge they have and the corresponding potential phi at point r, and then plus q. This is the summation of all the thing, and this is phi and r plus d. Again d tends to 0, that is the condition we should have. Now, normally d is very small compared to r magnitude wise. Then phi r plus d, that quantity, I simplify, and like before last class also I did this same technique. It should be simply d dot the divergence of phi, the gradient of phi at r, and I should not extend much because it should be the higher order of d, and I can neglect safely. So, u d is now minus of q phi r, and then plus this quantity plus q of phi r and plus q d dot r Okay. Now again I have this QD term, Q dot D, that is the dipole moment P. This term are going to cancel out, and simply we have dipole moment P dot the gradient of phi at some point r, and this quantity is nothing but minus of E at point r. So my potential energy that the dipole should experience due to the presence of this external field is simply minus of P dot E. Okay. Now whatever the since it is experiencing a electrostatic potential energy then due to the external field, so some sort of force it should exert this external electric field, so that again we can calculate. So the force on the dipole dipole due to the electric field, external electric field. So what is the force that the dipole going to experience? Now I know what is the energy, right? So the force should be simply minus of this quantity, this potential energy. Okay, and this expression I already figured out, so it should be minus of the gradient of, then again minus of P dot E, and I can absorb this minus. So F simply becomes the gradient of the scalar quantity P dot E. Now I can use a vector identity here. This is a very important vector identity when we have two two vector field here, then the vector identity that follows like this. So that I can write is, if I extend the vector identity means I am saying this, I have that I want to find out the divergence of two vector quantity, say vector field F dot G. This is, so this quantity we know that this is not a very straightforward thing, and it should be like here I am writing directly. So it is okay, let me write it first here. So F dot this over G, there are many terms, be careful, and then E dot this operator that will operate over F, and then I have F curl that is operate over G, and I have G and then curl of F. This is not a very straightforward, I must say, and that we are going to use here. So that my first term will be P, this will operate over E, and then E dot these things operate over P, and now P curl of these things and E curl of these things. Now, if you look carefully, many term will cancel because P is, fortunately P is a constant. Since P is a constant, so this operator over P does not mean anything, so this term will 0. Curl of E, we know that it is 0, and curl of P again it goes to 0. So, simply we have F is equal to, which is divergence of P dot E, and that quantity is P dot this operator that will going to operate over E. So, this is roughly the expression we have. Okay, now for uniform E, now let us consider the E is uniform. Okay, so now E is uniform. So, for uniform E, that is uniform E means it is simply constant, then simply I find that this operator over a constant, so it is simply gives 0. So, that means I should have F to be 0. So, what is the conclusion? The conclusion is there will be no translation motion of the dipole. There will be no translational motion of dipole under constant E. But what about the torque? And that you find that that we will get something. So, next we calculate the torque. So, for uniform field we find that there is no translational motion, but for uniform field the force on charge plus q and minus q they are equal and opposite. So, that basically creates a torque. So, what should be the scenario? Let me draw it. So, this is suppose the constant electric field moving in this direction, and I placed a dipole, tiny dipole, I magnify that, and this is one charge and this is another charge, and this charge is say plus q and this charge is minus q, and when we have a constant electric field, so the force that it will experience is simply q multiplied by E, which is in this direction, but because of this minus sign here it will experience a force in the opposite direction, which is minus of q E. These are equal but opposite. So, obviously it should experience a torque. If it is a theta, then it should experience a torque, and that we can calculate the torque tau. We know that if we know the potential, then the torque can be calculated, the derivative with respect to theta, okay, and that quantity is simply minus of del del theta, and ub we know it is P dot E. So, it is simply P and then E and the angle between these two, which is cos theta. This is cos theta. And let me write cos properly. Cos theta. So this is simply, if I make a derivative with respect to theta, it is P E and sin theta. In vectorial note, this sin theta can be absorbed, and I can write it is simply P cross E. This is the amount of torque it is going to experience by a dipole whose dipole moment is P, and if it is placed an external electric field, constant external electric field E. Okay, so also we calculated the potential last class, and then we try to find out the electric field out of that. That was the homework, if you remember. So in many books it is written in terms of polar coordinates. So I can also calculate this. We can also calculate this in polar coordinate, but in this gradient form. So a dipole potential as a gradient, if I want to write, say phi r is 1 by 4 pi epsilon 0, and then P dot r divided by r cube. That was the potential we calculated, and also we did it in gradient form, if you remember, by using this tricky method, and it was 1 by 4 pi epsilon 0, and it should be P dot the gradient of 1 by r, where this, I believe you can check by yourself, that gradient of 1 by r is simply, okay, I should put a negative sign here, is simply minus of, okay, so it is simply minus of 1 r by r cube, or 1 by r. In a vector form it is r by r cube, or unit vector divided by r square. This is r. Okay, I am not, the pen is not working properly, but this is, say, r vector divided by r cube. So that I use here to get the potential. Now the E I figure out from that. So my E, electric field due to dipole, is minus of the gradient of phi r, and I simply have, if I simply put this one, then it should be, okay, so let me do that. Okay, I can use the old, so minus of this, and phi r, if I use this one, it is simply one by 4 pi epsilon 0 and P dot r by r cube. So that quantity I can manipulate and try to find something. So minus of 1 by 4 pi epsilon 0, and then it should operate, the operator should operate over the quantity P dot R divided by R cube, and that quantity I can expand to find 1 minus 4 pi epsilon naught, and I can expand, it is a vectorial, so it should be 1 divided by R square, and then the gradient of P dot unit vector R and then plus P dot unit vector R and the gradient of 1 by R square. You can write this at R divided by R square, R cube is equivalent to unit vector R divided by R square. So, I use this one to get this. Now, this operator, if I write in polar coordinate, because dipole is placed in a plane, so I can write also in polar coordinate. So, in polar coordinate, the operator R theta phi, it is R unit vector del del R, then theta unit vector 1 by R del del theta, and then phi unit vector, I believe you remember the scaling factors. In that case, the scaling factor is R scale factor H1, H2, H3 theta, and then del del phi. That was the expression. Well, now I operate this R theta phi over P dot unit vector R, and that eventually gives me operator R theta phi, and P dot R is simply P cos theta, right, because the angle between R and P is theta. So, that quantity is depends on theta. So, all the other component will not be there. So, it will be simply 1 by R. So, it is 1 by R, then the theta unit vector, and I have del del theta. So, it should be P and then sin theta, the derivative will be sin theta with a negative sign. So, eventually I have minus of eventually we have minus of P by R and then sin theta and then theta unit vector. So, this is one component. Okay. Another component is still there. So, I figure out this component, and another component is still there, and that again we can execute. So, if I do that, then the gradient in R theta phi 1 by R square is simply R unit vector del del R of 1 by R square, and that quantity is minus of 2 and then r cube and r unit vector. So, the overall E I can now write as a function of r, and that is 1 by 4 pi epsilon 0. It is in polar form, mind it, and it is 2 p and then cos theta divided by r cube and r unit vector plus p of sin theta r cube theta unit vector. Mind it, now I write my total electric field in terms of r theta phi coordinate. Phi is not there, only r theta is there because it is a two dimensional electric field. But let me go back to here, this is 1 by r square and this quantity, so it should be 1 by r cube, and this quantity p dot r I calculated, and that, okay, let me check. This operator p dot r I calculated, it should be p cos theta, and then I have sin theta. Yeah, p dot r is cos theta, and this, so I write the next term first. So here p dot r is p cos theta, and 1 by r square is minus of 2. So I should have a minus sign. So this minus is absorbed here, and other is minus, so both the minus sign is absorbed. So I write this term here. So this is my, so this is my one term and this is my second term, and this term I write here. This is my one term and this is my second term. The second term I write here like this, whatever I get, p by r sin theta. So p by r square, already 1 by r square is there. Yeah, it is fine. So now I can simplify a bit because it is r cube is sitting here. So it should be 1 divided by no, p is also there, so I can take p outside. P divided by 4 pi epsilon naught r cube, and then it should be 2 of cos theta r unit vector plus sin theta theta unit vector. Okay, so this is the expression of the electric field due to a dipole, but in polar form. A similar expression you people should we calculated in other form where we didn't so that was the homework. So let me write it that as well, that what was the expression we got earlier, and that expression let me write side by side so that you can realize. So that expression you supposed to calculate from the potential, and that was this 1 divided by 4 pi epsilon 0, and here we had 3 and then p dot r unit vector divided by r to the power 5, and then minus we had p divided by r cube. That was the expression we derived. I mean, that was the homework, but this is another expression but in polar coordinate in r theta phi. coordinate system. Now, what is the advantage of that? Because whatever the field line the dipole have, we can find out the expression of that field line. So, quickly let us understand that. So, the field line, if I want to calculate what is the expression of the field line due to the dipole, because if two dipoles are there, plus and minus, plus q and minus q, so there are some field lines like this and like this. So, this expression of this field line one can figure out what is the expression of this field line in polar coordinate, because the electric field we know. So, I can try to let me. So, if I have a line element like this is the line element dl, and if this angle is say d theta. So, the line element, this line element is the line element I take for this, say whatever the this is the line over these field lines, the line element I take over this field line. So, dl in polar coordinate it is simply r unit vector dr and plus r d theta theta unit vector. So, this is the way the line segment we write in polar coordinate. This line segment I took over these field lines produced by this dipole, the system of two equal and opposite charge particle. Now, the electric field, the components are known, right? Er r unit vector plus E theta theta unit vector. What is Er and E theta? Because I just calculate here. Er is here, I can write it, I need to check what was Er here. So, Er is P divided by 4 pi epsilon 0 r cube and then 2 of cos theta, and E theta is equivalent to the same quantity P divided by 4 pi epsilon 0 r cube and then sin theta. These are the two components of E. Now, if I want to find out the expression of these field lines, I need to have a relation, and the relation is on the field line, so this dl vector and this E vector, they are parallel, right, because that is why we calculate this on the field line are parallel. So, if two vectors are parallel, so these vectors, so dl vector and E vector, they are parallel. So, that means their components, the ratio of their component should be same, and that if I write dr divided by Er is equal to r d theta divided by E theta. That basically gives us the relation, and the relation is saying that dr divided by r is equal to Er divided by E theta then d theta. And now integrating this, I can have, so what value we are having here. So, this is ER is 2 ER divided by E theta. So, P divided by these things will cancel out. So, we have 2 cos theta 2 cos theta divided by sin theta, and that d theta, and that I can write that 2 of d of sin theta divided by sin theta. And now if I integrate this entire stuff, I can simply have that is equal to some constant k. So, I simply have r is equal to that constant multiplied by sin square theta. So, that is the expression of the field lines that is created by the dipole. So, what kind of field lines? So, the field line looks something like this. So, I have 2 dipoles here, I have a dipole here, and the field line, say, suppose this is plus q and minus q, and the field line is going like this, and the equation that we get is simply r is equal to polar equation, r is equal to c sin square theta. And then it goes like this. Going outward. This is the way the field line is distributed, and this is the dipole, and this field line, the expression of the field line we try to calculate here, and which is this. So, today we do not have much time to elaborate more on this issue. So, I would like to conclude here. So, today we learn how the dipole is behaving in external field, how I can write the expression of the dipole, say electric field due to the dipole in terms of polar coordinate, and what should be the field line, what is the expression of the field line by exploiting the polar coordinate expression of the polar coordinate of the electric field that is produced by the dipole, etc. So, next class we will start another important thing, which is called the multipole expansion, and in that expression and that calculation the concept of dipole will be there. So, on beforehand we just discuss about the general thing of the dipole, but our main aim is to find out what is in the multipole expansion. If charge distribution is there, and if I want to find out the electric field, then this electric field is nicely I mean systematically I can expand this electric field as a contribution of the monopole, dipole, quadrupole, etc. So, that thing we do in the next class. Thank you very much for your attention, and see you in the next class.